So we talked about a big external magnetic field and how we're gonna put all the sample into that magnet, and then the magnetic field lines are gonna go through the nucleus and they're gonna interact with the little nucleus magnet. It turns out that there are other magnetic fields inside molecules. We're going to talk about the first one today, and then when we go back to look at chemical shift, we're going to talk about some more of them. All right. And so these other magnetic fields are called local magnetic fields because they're magnetic fields from inside the local molecule that has the nucleus, not from us outside. Those are external magnetic fields, right? And local magnetic fields, the first thing I want to talk to you about is the phenomenon of what we call shielding, okay? All right, so to start with, I want to talk to you about what if you had a nucleus, it was totally by itself, so it had no other nuclei nearby, because those give off magnetic fields, right? So it's isolated, and it had 0 electrons around it. So just be a nucleus, okay? In that case, we would call that a naked nucleus. It's totally uncovered, exposed by itself. That's the term we use, okay? And what we would see if we took that naked nucleus, we put it into an external magnetic field, then the net magnetic field that this nucleus would feel would be exactly the same as the external magnetic field. There'd be nothing to interfere with that, okay? And so you can see I've written that as an equation. The net magnetic field, B net, would be exactly equal to B external, okay? Now, if this were the case, then what we would find is if we had a whole bunch of these nuclei and they all behaved like they were isolated, then they would all absorb because their net magnetic field would be perfectly identical. They would all absorb at exactly the same frequency because the magnetic field would be the same size. So delta E would be the same size. So therefore the frequency would be the same size. And that would be totally useless to us, okay? All we would be able to say is, oh yes, this molecule has nuclei. And I think that's a given, okay? Fortunately for us, when we have atoms in a molecule connected by covalent bonds, atoms with covalent bonds have electrons around them, right? At a minimum for the covalent bond. So like if we look at a hydrogen atom, when it's covalently bonded to carbon, there's a cloud of electrons around the hydrogen. So I'm going to draw a picture here, and I'm going to kind of try to talk when I draw it. And it's not going to be a great picture because I'm not a great artist, but I have a rough idea of what I want to draw. So that's going to be our nucleus. And what we're going to have is kind of surrounding the nucleus, and I'm just going to represent it as like a circle like this, okay? That would be an electron cloud. It actually would be a sphere, but I just want to represent it as a circle, okay? And we would have next to it, and actually I usually draw these in blue also, so let me do that. We would have a large external magnetic field. Okay, so we've taken the nucleus, we've put it into a magnet. Now it turns out that charged particles, when you put them into a magnet, they get a force on them. Okay, and there's a rule for it and whatever, but the net effect is if you have a particle and you put a force on it, that particle starts to accelerate and move. And that's what happens here. These particles circulate, these electrons circulate around the atom. Okay, so this is a physics thing. Take a charged particle, put it in the magnetic field, they're just going to naturally start moving. Okay, but the significance of that is that when those electrons circulate, a circulating charge, a moving charge, also creates a magnetic field. That's another physics thing. So eventually you're going to learn electromagnetism in physics, and you're going to learn about this. And then this is how, like, we make electric motors and how we generate electricity and do all sorts of cool stuff, right? Okay, so this has a magnetic field. So what do I have here? I have, these are the two components, right? The electron cloud moves, and then there's a magnetic field. All righty, here's the thing. When you do the physics rules for this new magnetic field, the new magnetic field, because electrons are negatively charged, they go in a certain direction. A magnetic field goes in the opposite direction from the external magnetic field. Now, it doesn't look like it because on the outside it's going in the same direction. But what we're going to be concerned about is inside the nucleus, because that's the field that the nucleus feels. And you see, inside the nucleus, right here, direction. Do you see that? Okay, so I'm gonna draw you another picture. By the way, I just want to put a term here. I said created, but physicists use a different term. They say it's induced. So it's caused by. So it's called the induced magnetic field. Look like, well, that's a super extra complicated picture. Let's draw a simpler picture that basically says the same thing. If we draw the simpler picture, what we get is something like this. Again, here is our external magnetic field, okay? Here is our nucleus, and what we are getting is, then you see it points in the opposite direction. It goes right through the center of the nucleus, and we have a symbol for this. It's a B because it's a magnetic field, and we call it B sub S. That is what we call the electron shielding. Shielding is a magnetic field. Clouds generate their own magnetic field. It goes against the external magnetic field. Now, why is that important? Magnetic fields add up. Like if I have one magnetic field, I put a second magnetic field, the total magnetic field will be the sum of those. We'll add them up. But they add up as vectors. Okay? And the reason for that is that magnetic fields have not only a magnitude, right? A size, could be little, could be big, okay? But they also have a direction. It could be up or could be down, for example, okay? And so whenever you have something that has a number with a size and a direction, you use a vector. And then when you add those numbers, you have to do vector addition. Now, last semester in lecture, we briefly touched on vector addition. If you've taken physics, you start doing vector addition from the very beginning when you do Newtonian mechanics. But if you've never seen this before, vectors are pretty easy to do. What we do is we use the arrows. So this would be the arrow that represents the external magnetic field. And then we start sort of lining them up from we start at the back of one arrow, we point toward the head. Then we take the back of another arrow, we put it there at the head, and we go to where its head is, and so forth, okay? And what happens in this particular case, then, if you look, external magnetic field, it's actually millions of times stronger than the little shielding fields. I just haven't drawn it to scale. And then you have the shielding field. So to add it, we go up to where the big magnetic fields, we start there and we put the shielding magnetic field next to it. And so the vector sum is equal to B external plus B shielding. It's just that because B shielding is in the opposite direction, it acts like a negative number, so it takes away from B external. Effectively then, if we really think about it, what the shielding magnetic field is doing is it's making the overall magnetic field smaller. It's like it's protecting the nucleus so that that nucleus doesn't feel so much force from the external magnetic field. We say it counteracts that extent, okay? And so because it's sort of protecting or counteracting that, they said it's shielding the nucleus from the external magnetic field. That's where shielding comes from. Why is that important? Well, the size of B shielding is not a constant. The size of B shielding depends on the electron density of the circulating electrons. So if you have a lot of electrons, a high density circulating, you get a bigger magnetic field. If you have only just a little bit of electrons circulating, that shielding is very low. So therefore, what happens here is if B shielding gets bigger, B net gets smaller, the delta E is proportional to B net, right? So it changes the delta E. So as the shielding changes, the delta E changes. And so I'm going to draw a kind of a complicated looking at first graph. So here we're going to have potential energy. Down here, what we're going to have is B net. And we're going to say in this direction, it decreases. We're going to start on the left. We're going to imagine that we have a naked nucleus. And what we see is when you have a naked nucleus, then the net magnetic field is equal to the external magnetic field. So I'm saying here's the net magnetic field, here's the external magnetic field value right there. They're the same right here when the nucleus is naked. And at that point, then you're going to have your biggest, well, not necessarily, but you're going to have a big delta E, right? Then we start shielding. And what that does is that makes the net magnetic field smaller. So over here, what we have then is from 0 electron density, we go to low electron density. And over here, we have high electron density. Okay, so what happens? Well, in this region, we have our largest delta E. So we're going to call that frequency H nu 0, the frequency that the naked electron absorbs in the magnetic field, okay? And that's because that distance is big, nu 0 is going to be. So what we have up here then is we have high frequency here. We go in that direction. If we go in the middle, if we look at sort of here's one with kind of a low electron density, we would have delta E1, that's H nu 1, and nu 1 is going to be smaller than nu 0, right? Because that distance is smaller and it's proportional to that distance. And if we go over and if we have a really high electron density, H nu 2 and so on, right? So these frequencies are lower. So as we shield, the frequency that's absorbed gets smaller and smaller and smaller. Okay? Now, there's one other thing. It didn't. I didn't get it in these notes. I'm going to put it here, but we're going to. So what we talk about with frequencies often is what's called a frequency shift. So we can measure an absolute frequency, or we can take one frequency, then take another frequency and compare them. And the difference between those is called our frequency shift. And we're going to see when we do the chemical shift, hear that term, shift, we're going to see that that's actually what we measure and calculate from in the NMR is the frequency shifts, not necessarily the absolute frequencies. All right, be that as it may, there is an important frequency on here. It's this frequency right there, frequency 0, which was the frequency of the naked nucleus in a given magnetic field, right? And that frequency is called the fundamental frequency of the instrument. And I say of the instrument because an NMR instrument has a magnetic field, of a certain size, okay? And when we put the sample in, that then sets the fundamental frequency of the instrument. And the instruments themselves are generally classified by the value, the approximate value of their fundamental frequency. So again, really small, super old instruments were maybe 40 megahertz. They had small magnets. Then you could get bigger magnets, 60 megahertz. We have a non-functioning, because it doesn't function electronically anymore, but we have a non-functioning 60 megahertz instrument that's very old. I'll go take a picture of it, of the instrument sometime and show you the magnet. When I go in next week, I'll take a picture. But modern instruments use superconducting electrical wires to create really big magnetic fields. And you know, a small modern instrument that might be used in research would be like 200 megahertz fundamental frequency, and then they go up from there. All the spectra that I took in my research were on a 400 megahertz instrument, which at the time was a pretty large instrument. And as I said, we had a 600 megahertz, but we weren't allowed to touch that. It was for special thing like protein NMR and stuff like that. And I've heard that now they have 800 and maybe even, you know, 1,000, which is like a gigahertz. You know, basically at the time, and this was 30 to 40 years ago, these instruments were extremely expensive. And so there was sort of a rule of thumb. Every 100 megahertz was $100,000. Excuse me. So, you know, our 400 megahertz instrument was a $400,000 instrument, and it was owned by the Stanford chemistry department, and we all shared it. We signed up for time slot appointments to be able to even use that thing. Anyways. So what we see then is that what shielding of the nucleus does is it causes the nucleus to absorb at a lower frequency than the naked nucleus, right? It's a lower frequency than nu zero. And so shielding then is one of the factors that contributes to the chemical shift, which we're going to talk about later. It's the only one really that we talked about up until now, okay? But what we're going to see in a later section of this advanced NMR is that shielding of a nucleus, is that molecules have other magnetic fields in them. And those other magnetic fields also contribute to the net magnetic field. And so they also shift the frequencies. And so the chemical shifts that we have on our table are a combination of the shielding magnetic fields and then other magnetic fields that we're going to discuss later. And so that's why our table becomes really complicated. But the flip side of this is that, in a sense, what we are indirectly measuring in the NMR is the size of the magnetic field that's on the nucleus. And to some extent, that gives us information about the electron density around that nucleus. And then we can relate that to structure, right? If we put electronegative atoms near, the density goes down. Okay, so then we get a certain absorption.